Professor Satoshi Matsuoka, who is honoring us with his presence year on year, which is an absolute privilege. Well, go ahead. Thank you.
Okay, thank you for the invitation to come here, despite the fact I'm only here for like 30 hours. I go to Singapore.
That's more than usual.
Yeah. Go to Singapore, stay for 30 hours. Go home, stay 30 hours. Go to SC Asia in Sydney for 72 hours. But you know, it's a real pleasure to be first time in South Island. I've been New Zealand. All my trips have been to the north, and it's lovely nature. You know, vegetation looks very similar to Japan because geographically, I think it's very similar. Yeah, so it's very lovely, except there are fewer people than Japan. Yeah. So today, I'm going to talk about what we are doing right now, as well as our, what our direction is forward. Now that we have this machine that's been running for like over 3 years, very successfully. It's a very large machine, Fugaku, which occupies about 3,000 square meters, which is sort of a small hyperscale size, a small hyperscale data center. But since it's very dense, it's got 160,000 nodes in total, or about 8 million. Nearly 8 million ARM cores. It uses about 16 megawatts, so it's very, very efficient. When you divide 16 megawatts by 160,000, it's about 100 watts per node, despite the fact it has HBM, has 48 cores, and it has a 5 to 12-bit times 2 SVE vector instruction set. Also, it's very reliable. So we only get maybe one node failure per few days. So throughout the year, the hard sock failures for a node amounts to about a few hundred, which means that the MTBF of a node is about 1,000 years. So so for a user, it's very difficult for users to see any failures if you are a user. As a system administrator, you might see some, but it's a very reliable machine from the user's perspective. So it's gotten awards and like top 500 and all that, HPCG, and we got Gordon Bell Awards and various types of awards. So it's been very successful, but of course the real contribution is in the application. In fact. Since I talked a lot about COVID application in the past, today I'd like to talk a little bit about this application that's already running on Fugaku. In fact, it was running 2 years ago. That's more of which is one of the topics of this conference, this edge to the cloud, or this computing continuum type of application running on Fugaku, which became the Gordon Bell finalist in the climate modeling category in 2023. It nearly won, but it was an honor just to be selected as one of the finalists. So the application was to try to predict very ultra high resolution weather from the radar scan in real time with this most advanced radar system that are being equipped in several places in Japan. So usually the weather forecasts are like coarse grain. The forecast you see typically are typically in the range of 5 kilometers to going down to 2.5. But then you can't really resolve the clouds because the clouds have to be modeled deliberately rather than being simulated directly. So with a machine with the power of Fugaku, you can actually do this high resolution type of weather simulation. But also you need to simulate it in real time with high resolution scans of the sky. So in fact, there's a perfect instrument for this now. It's called a phase array radar. It can scan the sky with 100 different types of more than 100 different frequencies all at the same time. And it can scan the area of about 50 to 100 kilometers So just placing one radar in your metropolitan area will allow you to do the complete sky survey, the weather survey of the sky in real time. So what we have done is to combine this, the instrumentation. You get very, very high resolution and high bandwidth data coming from the radar. And we have a petascale weather simulation, advanced weather simulation running on Fugaku using about 0.5 million cores, about 500,000 cores. And then we would do a real-time data simulation with 30-second forecast cycle. Okay? So, and then once we get the forecast, we would ship the forecast onto our collaborating web services partner, application partner, and they would multicast your personalized weather forecast data onto a smartphone, because these forecasts, of course, can be location aware. So they can tell you, it's going to, where you're standing, it's going to rain, like torrential rain in 30 minutes. And this was designed for the Tokyo Olympics, which unfortunately, which was supposed to be held in this really hot summer humid days in Tokyo. So something like this would have been potential. But due to COVID, unfortunately, Tokyo Olympics was held without audiences. So this system not quite didn't serve its purpose, but still, we did experiment and worked really well. So this is a sort of a cartoon of what we were doing. So there's a 3-hour update, outer domain using 2,000 nodes, doing 1.5 kilometer resolution. But then doing an inner domain, 30-second update, which is really hard because you got to do this real-time update and real-time data simulation every 30 seconds. And then, so you'd be running scale, which is a high-resolution weather forecast, and then using a common filter-based data simulation. And these will be used on about 9,000 nodes on Fugaku. Okay? So this was done in practice. But early in the panel, I criticized the smart city experimentation just being dropped in rather than doing any sort of a simulation. And this is exactly what we've done. So I'm being very self-critical. But being self-critical, later on, the team basically went on to do what was supposed to be done, which is to, now that we have confirmed the validity of this simulation, we can now synthesize weather and do the simulation experiment to see how many of these radars, these advanced radars, we need to do full-fledged forecasts throughout the country. So this was just done for the island of Kyushu, which is still fairly big. So they did the analysis, they did the simulation, they did the analysis, and these are one of the proposals. So by placing approximately about 15 radars, 15 of the radars throughout this fairly large, one of the larger islands of Japan, so for the country, maybe about 70 to 80, maybe about 100 radars, you can do this 500-meter real-time forecast. So this is sort of so this is the correct engineering that was supposed to be done, but now we have the capability to do so. And also, National Weather Bureau, or the National to be exact, the Meteorological Agency of Japan, they use Fugaku to also to do real estimation of these ultra fine resolution weather forecasts, but to focus on predicting these torrential rains, because these torrential rains are becoming a societal problem, not just in Japan, but also in Europe. There's a lot of flooding in Europe, flooding here in New Zealand. So do we have the traditional forecast? This is 5-kilometer resolution. Is way off compared to this is what's been observed. So they did a lot of work to not only to reduce the resolution, but also to do much better modeling of the phenomena, and they were able to now able to achieve this ultra high resolution, but also very accurate prediction of the torrential rain. They liked it so much that there are now bought copies of Fugaku, and And they bought 2 copies, not just one. Well, not the full system, but good enough for their purpose. But they bought 2 machines. And when the Weather Bureau buys 2 machines, it means they're serious. Right? It's not, they're no longer experiments. They will put this in production. That's why they have 2. Because any good Weather Bureau will always have 2 machines as a backup. So this means they're serious, and we will be getting, what I hear is starting this year, we'll get this high resolution forecast that will be used to predict these torrential rainfalls throughout Japan. So, okay, so those are just exemplars. There are many exemplars of realistic sciences that are being done on Fugaku. In fact, security alert. Okay. Well, so we commissioned one of the consulting companies, in this case Hyperion Research. There are 2 companies, there's Intersect 360 and Hyperion. But we commissioned Hyperion to do investigation as to what's the economical impact of a machine like Fugaku. And the result was astounding even to us. So, Fugaku cost about $1 billion to build, more than $1 billion to build, to design, build, and operate. But it said that the financial gain, the potential financial gain for the society, is about 102 to 135 billion US dollars, which is about nearly 2 orders of magnitude more than the investment value. So the return on investment in this case is humongous. But I guess that's because now, like I said in the panel, now these very large supercomputers are becoming real by being able to create these tangible digital twins, be it in simulation, but also in AI. And that now we can solve real societal and also industry problems, not just a very narrow scope of basic science or very selective sets of target problems, but very, very general. Can solve these general purpose problems. And so where are we going from here? So there obviously we are pursuing our next generation plans. Next, we tentatively call it. Sort of competing towards Zeta scale or whatever. So we're doing the science of high-performance computing, but also looking at science by high-performance computing. What happens if we have these capabilities? Also, obviously doing AI, but we're doing both science of high-performance AI, but also science by high-performance AI. What can we do? And that also combined with HPC with simulations. And by the way, I noticed that this meeting, despite the fact we have lots of experts, HPC experts, we haven't really heard the Q word, right? The Q word. So I'll say it now. Okay. So I know, Quantum, right? Yes, and they work with us, so that's great. So we're also pursuing Quantum-HPC Hybrid, not just pure quantum information science, but combining quantum and HPC. Also, we are trying to investigate what kind of application areas are amenable to significant, well, qualitatively different amenable acceleration by use of this Quantum-HPC hybrid technology. So the first project will be FugakuNEXT, which of course has not been funded yet. The feasibility study project has been funded, is ongoing. If all goes well, we hopefully will have a deployment sometime 28, 29. This keeps changing. But if we have the repeat of Fugaku, this will be another $1 billion, whichever currency. We'd like to be like US, but we'll see how it goes. Some $1 billion scale project, so it would have hopefully to have quite a bit of impact, a much bigger impact to the industry by looking at the technology 5 or 6 years forward instead of just 1 or 2 years. And then this science, AI for science, we have the RIKEN AI for Science, which will be launched in 2024, April. So in about a couple of months. In fact, we're already doing it. We're already running it in heavy preparation. So this will officially start April 1st, but the total funding over 5 years will be somewhere in the neighborhood of about $5 billion. And then we have the Quantum-HPC Hybrid, which has already been funded, and the Quantum-HPC has already been funded. In fact, it's already started. So we are funded for about $150 million to build an infrastructure that will combine HPC and quantum. So, and Quantinuum, by the way, is one of our partners there. So, along with IBM. So this is so in order to harness all these projects, our center is growing. Of course, all those projects, not just with RIKEN, AI for Science is a RIKEN project, not just my center, and there are many centers within RIKEN. But still, we're responsible for all these science of and science by. So our portfolio of people are growing, and in fact, we just hired a new person to deal with the digital twin or the Smart Cities initiative. We just formulated a Quantum-HPC Hybrid division. We are forming an AI for Science platform division, and we're hiring. We're being very proactive about having female leaders. So we're hiring new female PIs. So overall, we're growing. In fact, we're hiring very aggressively. So if you or your constituents or students or your or your sons or daughters are interested in working at RIKEN, we can't pay you a high salary like the industry, but it'll be an interesting place to work. So please spread the word. Okay, so one thing we're doing with Fugaku is to try to build a platform for science, because not just run singleton application. This was kind of mentioned in Eva's talk earlier, in that she emphasized the importance of establishing a workflow. So run on these machines is no longer about running these big, 100,000 node codes, although we can't do that. We have the technologies to do that. But on a regular basis, that's not what we want to do. So it's really need to build a platform. And I make an analogy to shopping, where the behavior of consumers totally changed in the last 10 years, thanks to Amazon. And that, it used to be that the people just shopped around these individual storefronts. But now people go online, and there are various virtual storefronts. And then there's Amazon Web. It sits on the cloud, whatever web service or any sort of cloud infrastructure. But the point being that all these distributed information, disorganized information, now gets unified into the platform, and that's how Amazon runs its recommendation system. That's how they make their operations more efficient. That's how you can be offered, for the consumers, you can be offered all these choices that were never possible before. So, and that's why Amazon Amazon has grown so rapidly. So science that is now very much digitized, but still is, compared to like consumer shopping, is still behind. So you'll still have individual labs, and the labs communicate by these arcane methods of writing papers. Okay. Well, of course, you can argue now it's digitized, it's on archive, and you can let the AI read it and summarize. But still, there's lots of human labor involved in writing a paper. So instead, the future platform should be much more sophisticated, and that we have a digital platform based on supercomputers either in supercomputing centers or the clouds. You have the various platforms of science, depending on your application domains. And here, all the knowledge and the data are accumulated. And in fact, some disciplines already do this, like high-energy physics is a typical area. But that type of assimilation of the data into respective platforms sitting on a common infrastructure and running both simulation workloads, AI workloads, whatnot, and also the data sets all combined is sort of the sharing of knowledge you do amongst the scientists, and not just by papers. So this is sort of a direction we're going to. So we're looking at several domains. We're targeting several domains to build this type of platform. So one platform, I'm sorry for some of the Japanese that's still left there, is a pharmaceutical platform that's being led by Professor Dr. Okuno, who's one of our division leaders. So what they're doing is to build this pharmaceutical pipeline that their team hopes to accelerate drug development from being like 10, 15-year ordeal to just 5 years. And of course, in fact, there are, if the society is in crisis, there are live evidences actually you can get these pharmaceutical developments be done in very rapid time. COVID vaccine was one perfect example of that. But normally, that's not possible. So you have to go through all this from the target identification to discovering the effective compounds that would match the target to all the way down to the clinical trials. So of course, the dream is to digitize the whole process, but of course, they will be difficult because we have to create a whole entirely digital human being, which is a digital twin, which actually we were partially successful, but I won't go into that today. We have digital hearts, and we have digital respiratory system. We have digital brains, digital twins of brains now on Fugaku. Very accurate one that can be used for clinical trials, for clinical situations, but still unproven. So right now, his team is focusing on this target identification, and also to discover the compounds. But these alone, the front end of pharmaceutical pipeline consists of more than 50 components. Some are simulation components, similar to the ag. Some are AI components. Some are data components. There are many, many, many components that are interacting in a workflow, and more, in fact, very sophisticated workflow to constitute this pipeline. But a lot of pharmaceutical companies are involved in this project. So once this pipeline is complete, it's almost done. Some of the stuff are already constructed, and almost at least the prototype is already done. And once these are constructed, we're hoping this will it'll be not only a benefit to pharmaceutical companies, but also for other life science. It can be a template for other life science type of applications. For example, farming, like the food production of farming. Very, very similar pipeline. So that's one thing. Smart cities, we're not only doing simulation studies, but also we're trying to create data management system to combine the relevant data from earthquake, from all the simulations to a lot of the data that are incoming, that are on sensors, or that have been recorded statically regarding the structure of a city, from the geography to the buildings to the sewage to everything. Okay? And then we can run simulations on top of it and see what the evacuation plan should be, disaster response should be, etc. So in fact, my point was we have all these technologies. We have these technologies to create this digitized smart city environment. So so our big project now is to how to combine these technologies in order to be able to create an effective digital twin. And as has been for auto driving, where one of the reasons why the cars don't drive around anymore, in order to capture all these digital driving situations, is that these live camera situations it's very difficult to recreate these extreme events, like somebody suddenly leaping in front of a car, which really doesn't happen, but you're supposed to be able to cope with it. Same with smart cities. So it's okay to model like the mundane everyday occurrences of events pertaining to a city. But what we really want are either these extreme, sometimes these extreme events like natural disaster hitting a city, or even like or even smaller events like maybe some local crime happening or building burning, or burning buildings, where it's still abnormal enough that there has to be some emergency response or some sort of response that needs to be necessary, and that's where all the resources need to be deployed, and that's when you really need to see if the plans you have made or will work, or in fact you need to make the plans to make sure that you can combat these types of these extreme events. Okay, so that's what we're trying to do with various companies, and I won't name them, but that's what we're trying to do with several companies, and also with the expo, upcoming Osaka Expo in 25. We're trying to demonstrate our capabilities, and so in fact, that type of platform will transcend will transcend a single machine. In fact, is to serve the society. So one thing we're doing with Amazon, with AWS, is to firstly notice that their Graviton processor, Graviton 3 now, Graviton 4, it could be binary compatible with Fugaku's X4FX. In fact, we collaborate with Amazon to test various codes, various compilers, various libraries, various applications, and they're amazingly compatible. They're just like AMD versus Intel, despite this little differences in SVE, but they're essentially compatible. In fact, they're almost performance compatible. So Amazon has done a great job at creating a processor that's performant. So what we're doing with them now is not only to port our applications, but port the entire Fugaku's environment onto Amazon. So we can recreate Fugaku's HPC programming and also execution environment, development environment onto AWS. Yeah, so those two environments will look like. And this is really important because despite the proliferation of HPC on AWS, there's not an established software stack that encompasses all the robustness and all the features that we have put into building the distribution image for Fugaku, which, by the way, is controlled entirely by spec, including our commercial software. So thanks to our collaborators at DOE. So we can recreate the image here, but we can transparently port by using containers in its entirety over to AWS. So we can create a satellite version of Fugaku that our Fugaku users can use, or people can download the image and create their own private Fugaku. And this is upcoming. It's still in the creation process, but Amazon is very much excited about this opportunity of being able to having an environment which is proven to be able to support a whole bunch of HPC applications. Okay, so that's with the platform. And now with AI. So there's been a lot of talks about AI for science, especially pertaining to HPC. So I won't go into too much depth as to what it can do. But still, this is a slide I stole from Rick Stevens at Argonne, because Argonne and RIKEN will be collaborating significantly on this topic. We just had a whole-day workshop a couple weeks ago. Ultimately, we can do things like surrogate models, foundational models, which are generative. We can generate like genomic sequences. We can create procedures for experiments. We can generate code. Ultimately, our hope, our objective of both Argonne's effort, but also RIKEN's AI for Science effort, is to create a AGI scientist. Not to put scientists out of work, hopefully, but to serve as a support that Ewa mentioned, although there is, I think, a definite chance that the scientists may go out of work. The more we put, we'll see how it goes. Now, I really don't believe in the story that these advanced technologies will make the human beings lazy. And that's been my personal experience. I've been in this business for many years, and now, after many years of service to the community, it's the busiest time of my life. So if all the advances were relieving me in work, I should be sitting somewhere on the beach and drinking Singapore Sling or something. But I'm busier than ever, so I don't believe in it. So, but still, AGI scientists is very important. Now, when you think of different science of AI versus AI for science of AI being more traditional computer science AI, I mean, they are very much related. In fact, the science AI for science does utilize many of the research results pertaining to, traditional AI research results. But still, traditional AI, when you look at any of the papers, there are lots of fantastic results, but usually they pertain to classical AI problems, like solving image recognition, natural language understanding. Large language models are just exactly that. But AI for science is very much like HPC for science. So the real objective is to solve scientific problems, not to solve the AI problem, but solve the science problem that are not, solvable otherwise. So that's the whole point. So most of the papers out there, or even the most recent papers that focus on traditional AI problems like natural language, obviously things pertaining to LLMs, are looking at textual problems, or images that are very much abundant in nature, and we understand what they are. But with AI for science, the difficulty is we're trying to deal with data that hasn't been the target of AI, like genomic sequences, molecular structures, and so forth. Of course, a lot of the techniques may apply, but still dealing with lots of new types of data structures. And we also need to associate that with natural languages, because natural languages serve as a glue, or semantic glue, when we have multimodal models. So we have different disciplines. How do they correlate? Well, if they're totally separate data, they don't correlate at all. But by making the trained model be multimodal, including text, they can be hopefully combined. But there's no assurance this will happen. Now, so traditional AI, since their data set's pretty much fixed, right? So there's heavy focus on training because of the fact that your merit as a scholar, a researcher, is to have a model that's better than the other model. Right? So you try to justify your work by saying my model's better than yours. Whereas in science, the research credit is on the new scientific discoveries. So there'll be heavy focus on inference, or how to use the AI, or the data may become really available, so static training may not be very useful. Rather, since in science data is updated continuously with data streams, real-time training, which is really hard, by the way, becomes one of the research topics. So being training-centric versus inference-centric leads to different type of architectural optimization points. So that's how we're thinking, how we design a machine. So to solve the AI problem, to solve a science of AI problem, not the AI for science problem, rather than the other way around. Do we need the same machine? Can we use the same machine, or do we need a different type of machine? Also, trustworthy AI is important, but on the other hand, I wouldn't say less, well, maybe being less important is an overstatement. But people still, since there's human in the loop, which works to your advantage, that there's inherent human in the loop, and the humans sometimes do tolerate inaccuracies. Okay? So the earlier statement that these results by AI should always be checked by humans. Yes, of course. And that's your safeguard against some hallucinations or even some criminal intent using AI. And there are quick fixes to get accuracy like RAG, which is dirty, simple, but it's a very good quick fix. Now in science, trustworthy AI is extremely of high priority because science needs accuracy. Now the fortunate fact is that because of the fact that we can have experiments, and this has been covered in some of the talks, but we can experiments and also simulations, which will largely give you some ground truth, some degree of ground truth. The process by which you would fine-tune the model can be automated. There's a potential to be much more automated than processes like reinforcement learning with human feedback. So that we're working on how to enhance Fugaku to do 100,000 node scale training on this more traditional AI, training deep neural networks and so forth. Also a new team by Yokota to train large language models on Fugaku. It's a combination of different people from different organizations. They're doing fairly well. Their current focus is to train a Japanese language model, and currently it's a combined work between Tokyo Tech, RIKEN, and Fujitsu. But the model is still, compared to GPT-4, is not as good, but it's a very small 70 billion parameter model, and it's at the top of all the competitors that are also training these Japanese models. But on the other hand, these AI for science techniques are being used already in many applications. So especially surrogates, when it's very easy to get the ground truth. In fact, ground truth is used to train these models. But the new trend is to combine these surrogates with more advanced simulation models that work in tandem to get better do better control of uncertainty. So sort of a real-time UQ in order to make sure that you have an accurate simulation that are accelerated by AI methods. So one such work is being done by a group at University of Tokyo using Fugaku. So essentially they want to do this massive scale earthquake simulations from epicenters to the topsoils to buildings and shake the entire big city like Tokyo. Okay. So in order to do that, they estimate if they did it with just purely by simulation, they need a machine that's like 10 exaflops at least, which is far exceeds the capacity of Fugaku for the moment. But they've been able to come up with an algorithm that's numerically accurate, so it controls uncertainty. Uncertainty by the use of these surrogates combined with simulations controlled, so there's numerical accuracy, but still achieves 25x acceleration, which will give it essentially 10 exascale performance for Fugaku. And also a similar work is being done, and this is like real-time response application, where instead of using the supercomputer itself to do these emergency computing, so to speak, instead the the neural network is trained beforehand. And then once a disaster situation happens, then you run the neural network instead of the real simulation to estimate, in this case, assess the damage of a massive flood that's occurring. And of course, this is a check for accuracy. In fact, they're building a system where the AI prediction, because it's so accurate, they are able to then, again, determine the per each location on the map what the flood levels will be. And this can be broadcast in real time, location aware, to cell phones to direct people to their safe evacuation zones. When tsunami happens, you run for your life. Otherwise, you die. So, but which way you run is important. Where do you run is very important. And even with Fugaku, if you do a real-time simulation, when earthquake happens, the first waves hit the wave sensors that surround Japan. Right? To do the real-time simulation takes 15 to 20 minutes. So, which is not quite enough, because tsunamis will reach the shore by that time. Whereas if we use surrogates, we can get the accuracy, but this calculation can be done in matters of seconds. So these urgent computing scenarios where you do real-time simulation in the face of disaster, that's plausible, but you know, a better preparation engineering is to use surrogates when they're applicable. And also, you can use AI being used for design optimization. This is an instance of our car design that's being produced by generative methods, not necessarily generative AI, but more parametric generative methods. But we try to design the car automobiles, and then we do the compute. Then we use optimization techniques, AI-driven optimization techniques to derive a car design that's optimal in terms of the aerodynamics, fuel efficiency, or electricity efficiency. Also optimal in terms of the navigation and steering, like resistance to wind shear. And then also the car should look good. And so this is for human designers to balance many of these parameters to come up with a car design that's industrially viable. They look good, they drive well, they're very efficient. That's what the car you want. But what are they? These human ingenuities are now being encoded into AI, such that it takes about a single car human designer of automotives can design somewhere up to 5,000, 6,000 cars throughout their, let's say, the 30, 40-year career. This technique allows generation of designs, car design, 5,000, 6,000 car design in a single week. Okay. So again, this is AI and simulation combined, replacing humans and their expertise. And I think Doug asked, materials. What are the materials you really want to synthesize? Well, so the answer for us is a lot of these biomaterials, like biodegradable materials, or heat-resistant polymers that comes from these natural sources, because they're very difficult. Most heat-resistant polymers are not bio origin, so it's very difficult to produce one. But if we produce one, if we can manage to produce, high temperature heat-resistant polymers, it will revolutionize the industry. Same with things like perovskite. Perovskite. Solar cells, right? Which is also sort of organic. So we are running, we are establishing an AI and simulation loop where of course we have extensive simulation capabilities, first principle simulation capabilities of these materials on Fugaku, very scalable. But you can't screen to 100,000 compounds. So we combine just like a lock, very similar to a lock. We combine various techniques, like we use generative AI, we try to solve some of the inverse problems using some of the AI techniques, in order and combine that with first principle simulations and experimentation to come up with these novel materials. So that's sort of again, combining not just pure AI, but combining AI and first principle simulation and experimentation will give you the real results. So you just can't focus on that to make these innovations. So we're hoping that we will establish this sort of a loop where we have, I'm sorry again for some of the Japanese not been translated, but we have some sort of pre-trained model, which potentially is multimodal, but we will have acquisition of real-time acquisition of data. Then we'll have very high, of course, very high training capability. But then we will try to, then we can do the inference, but the purpose of doing inference is not just to apply along with simulation to solve the real problems, but to drive this loop of refinement, to run this, whatever means of fine-tuning that will be done automatically. For example, it can be done by reinforcement feedback, checking the result with simulations and correcting the errors. And then also there will be, again, real-time acquisition of additional data. Then we can, improve the model, not just to fine-tune it, but improve the model with new data acquisition. So the goal is to really create this workflow, which is a generic pattern across multiple disciplines. Okay, so we'll be focusing initially on biology and material science, but the real goal is to establish this sort of loop, this sort of a model creation loop for each of the discipline. Now, whether this will, combining these models will turn into a humongous foundational model for science, or can we use each individual models to constitute experts? That's something to be seen, and that's being debated amongst us. But we'll see but at least we need to have ways for the models to be fine-tuned and updated using our experimental and simulation capabilities. Okay, so we're trying to write this white paper because when we built Fugaku, we wrote a white paper on why simulation is important, and we got the money. So we're writing this. We are updating our white paper, but also putting in a whole new section regarding AI for science. We got almost 100 volunteers to write this up. But if you're interested, please let us know. The first draft will be published like in a week or so, I think. But we will, but we'll continue to improve and update. We also need to enhance our AI capabilities. So we are putting in, because Fugaku is pretty much full. So, and although there are lots of AI being done in Fugaku and simulation, Fugaku is not necessarily designed to do AI, especially training, and also to some extent inference. So we are also adding a new cluster and tightly couple it with Fugaku, essentially the same software stack. It will not be as large as a dedicated single machine like Frontier or Aurora, but still we'll have some capability to allow us to collaborate with our peers, both in large institutions like DOU, or maybe like some of the European centers, or with the cloud providers. And we'll have enough capabilities on our side. And also this will serve as a prototype for our 28 FugakuNEXT machine, because this will be, the capability of this machine will be somewhere, we're saying like 8 in training and inference, maybe like inference like 8 exaflops. For FugakuNEXT, we hope to achieve something like a few hundred exaflops, or up to zettaflops of training capability, hopefully. So we'll see how it goes. But this will be sort of a prototype before that. A few words on quantum. So we do have a separate center within RIKEN whose job is to build a quantum computer. So they're working on various quantum computer, a real one. They have a cryogenic chip, done by Nakamura, who's the director of that center. But they're all working on other schemes too, like semiconductor-based, ion trap, cold atoms, you name it. But their principal job is to investigate various schemes of quantum computing, where our job is to construct a platform so that people who's interested in quantum computing or its application of quantum computing to real problems can come and combine that with HPC capabilities to come up with some substantive applications that will drive the next generation computing. So we have separate roles. Of course, we're collaborating tightly, but we have separate roles. Okay. In fact, this is a statement again by our good friend Rick Stevens. We need substantive improvements of physical qubit in terms of physical qubits and circuit depth. But most of all, we need good algorithms that go beyond the current crop of algorithms. In fact, this was enhanced by, again, one of our good friend and colleague, Thorsten Hoffler at ETH. And he and Matthias Streuer is also a very well-known physicist in quantum computing. Together they published a paper that said that in order for a quantum computer to exhibit any sort of advantage, they really need to achieve exponential speed up over existing algorithms. So something like Shor's algorithm is good because fundamentally it'll achieve exponential speed up, but something like Grover's algorithm is bad because they're only quadratic. And their argument, which I also support, is when you only have quadratic speed up, then you'll be quickly caught up by classical. So okay, so then how do you coming up with quantum algorithms that will exhibit these quantum exponential speed up is really hard. There aren't too many that are well known. But if we achieve that, if there would be algorithms and application areas thereof, which will, to which some problems that are still very difficult or even intractable in conventional HPC, we can certainly offload it onto a quantum computer. Now, of course, the scope of these algorithms may be very narrow, because again, because of the requirement of exponential speedup, there are at least a few that people are trying to resolve. For example, like catalysts. A lot of applications regarding catalysts and so forth. So we really need to think of a quantum future, or quantum hybrid future, and of course, there will be tons of problems. These will be more dominant. Non-quantum future, but because of if we have a real quantum computer, we can optimize our non-quantum machine not to execute these, which are mostly double precision floating point. So if we have a quantum computer, LINPACK will be dead, because most of the last standing applications regarding highly dense 64 matrix, high precision 64-bit, double precision, even higher precision floating point dense linear algebra is material science. So then we can ditch all the 64 bits and concentrate on AI. So the project's ongoing. What we're trying to do is to have sets of real quantum computers. We'll have a 133 qubit. Initially, we'll get the 133 qubit Heron machine from IBM on premise. And this will be tightly coupled with Fugaku on the floor below. It's the first time IBM shipping this large-scale machine to be coupled with a large-scale supercomputer. And we're doing tight coupling because there are problems, because the cycle time of these cryogenic superconducting quantum machines are very fast. Whereas kind of like Quantinuum machine, the cycle time being ion trap is really slow. So there'll be, but they require very careful tuning. They cannot be run automatically. So we have experts different expert within RIKEN who will be taking care of that machine. But this will be placed in Wako, which is near Tokyo. So it'll be about 600 kilometers from us. But because the cycle time is so slow, their fidelity is it's great, but cycle time is so slow, it's worth it to have it over the internet. The latency will not kill us. We'll continue machine. And of course, we'll have the simulators where you have simulators running on Fugaku. We'll get a separate GPU machine other than not the AI one. This will, again, a separate GPU machine, more or less dedicated for quantum computing simulation as part of the portfolio. And of course, we have the supercomputers on the classical side, doubling as a simulator, but also the classical machines. But the real emphasis will be building a software stack, or things that combine the programming, the code scheduling of resources, the workflow and everything that will allow these hybrid algorithms to act, not only to function properly, but also will run across different types of machines. And we'll be adding RIKEN's machines later on when they become stabilized. But the real crux of the matter is really need to have a common software platform, so people who's trying to invent these exponential speed up quantum algorithms can develop and actually try out these algorithms on different machines. Because when you think about it, why did HPC prosper? Because we had supercomputers from very early on, and a platform very early on. Whereas, in quantum, the platform is very poor. So that's what we're doing. So this is the machine that will be, it's not the real machine yet. We won't have the machine until 25, but that's the chip. And also IBM has a roadmap of going to like, hopefully, like billion gates and few thousand qubit machine by 2033. So hopefully they'll cross our fingers. Then we can, we'll be able to run real applications. But there are a lot of details that we have to overcome. But we'll see how this goes. Finally, FugakuNEXT. So we're working with various new. This time, as I indicated last year, we were working with not just the usual suspect Japanese vendors, but also with the usual suspect American vendors, including Intel, not just a company like Fujitsu, but also Intel, AMD, NVIDIA, HPE, and now with ARM. So, and I can't really talk about this much because there are too much NDA, there are too many NDAs involved. But one thing I would like to show, by the way, these are some of the benchmarks we have given to the vendors. And vendors are coming up with multiple proposals for working with us, actually, directly to, in many fronts, actually. There's a significant co-design going on. But to see, how some of the aggressive ideas, some of the mid-tier ideas, and some of the conservative ideas, how they would pan out with these first sets of benchmark apps. And of course, we'll be enhancing this this upcoming fiscal year. But their initial response is to take these apps, and then we sort of co-design different proposals, right, for thinking about what we could do in 28, 29 timeframe, and then come up with what the speed up would be, what the power would be, what the cost would be, and so forth. So we're getting those metrics. In fact, we already gotten those metrics, and some look very promising. But just give you, because I can't give you any of the details, I'll just give you a very brief overview of our thinking because time is running out. But when you think about it, you are either most of the HPC applications we have observed, not just those sets, but those that run on Fugaku and other machines. And it's been for a long time, and we even wrote a paper about it. Most of the HPC apps are memory bound by some means. AI training is usually compute bound. AI inference is memory bound. It may have compute bound sections, like when you have transformers, you're calculating the front end portion. When you're doing the initial calculations, it's compute bound, especially when you have very long set of tokens. But once you get to the fully connected layer, you're able to exercise the use of like KV cache, then it becomes totally memory bound, and this is well known. Okay, so it's always memory bound. Depends on whether you have a compute bound component. Depends on your algorithm and also, let's say, your input token. Okay. So what we're trying to do is to think about, instead of thinking like whether GPU is good or not, religious wars like that, but rather think about, okay, given a workload, how do we fit these workloads into the architecture, into the proposed architecture, and whether we need to innovate. And one thing I can say, and again, I can't go into the details, but one thing I can say is we really need to innovate with respect to memory, and this sort of resonates with Bob's earlier presentation, but I'll give a different stint on it. So what's the binding factor? What's the technological limit? Well, it's all about data movement energy. Okay? So going 3D is an implementation to solve that problem. Potential is a potential technology to solve that particular problem. But what we're really bound by is not whether it's 2D or 3D. What we're bound by is the fact that things like technologies like LPDDR or 2.5D like HBM will not cut it because their energy per memory transfer is too high. It's like 5 picojoules per bit. Maybe it can go down to 2 picojoules per bit, but when you talk to the HBM vendors, they say, well, no, in the future, this will actually increase when they go to HBM4. Okay? So not good, because in order to achieve tangible speed up, we really need to, when we want to reach something like, Fugaku is currently about 163 petabyte per second. But when we want to achieve something like 1,000, and we want to keep the power to be within like 10 megawatts, we need to be really realistically 0.5 picojoules per bit. And it would be ideal if we want to continue scaling to go down to 0.2 picojoules per bit. Okay, so and because most applications are memory bound, there's just no way escaping it, because you have to transfer, when you think of any sort of, let's say, CFD, unless you go to really, really ultra high order methods, you only have to load from memory, right? Compute, store it back to memory. That's your compute pattern. So going to like 0.5, 0.2 picojoules per bit is the goal, but it's really tough, because 0.2 to 0.5 picojoules per bit is exactly the energy value for data transfer for UCIe, which is a chiplet specification. Okay? So just moving data between 2 chips in a chiplet, when you have a chiplet, it's 0.2, 0.5 picojoules per bit. Okay? Just moving across 2 chips in the chiplet. So obviously 2.5D will not cut it, so we have to think of a real 3D configuration. And that's the principal reason why we need to achieve 3D stacking. Okay. So we're doing various things. I think we're doing various analysis. We're doing various analysis of what kind of precision do we need? Can we exploit some of the artifacts of AI, and we're thinking of various algorithms, or doing analysis on what kind of precision do we really need, or can we exploit some of the artifacts, like we have FP16, FP8, but can we have FP21, which will be a very reasonable size if you have FP10, FP16. And we're publishing papers about those and doing some forward-looking analysis as to what would be the performance and energy profile if we had these hypothetical architectures. yeah, the activity goes on. Good news is that looking at 28, 29, what the vendors think is what's possible, and what we think is possible, and of course we're in agreement because we work together. Most vendors have come up with proposals if you go the most aggressive route. There will be significant advances, especially in terms of advances in data movement. But these do not come for free. There needs to be considerable advances in technology, packaging, but also to be commercially viable, there needs to be standardization. There needs to be a party that's willing to produce some of these components. And as such, it has to have mass adoption, and as such, it has to be adopted by the hyperscalers and so forth. Fortunately, if things like AI may drive the industry, because, for example, you can build an inference chip with not just with high flops rate, but with extreme high bandwidth, but large enough to accommodate models that will occupy terabytes. Right? So like more than multi-trillion parameter model, but being encompassed in a single chip. That will be that'll be revolutionary in terms of industry, and that's sort of a technology that we are aiming for in order to accelerate AI, not HPC AI, and of course to some extent quantum. Okay, thank you very much.